Welcome back. As discussed earlier in this MOOC, the output of a PV system, as long as it's not a standalone PV system, is fed into the electricity grid or an electric power system. I realize that discussing all electrical engineering aspects of an electricity grid is out of the scope of this MOOC. Nevertheless, I would like to discuss a few operational issues in which photovoltaics will have an impact on the current or the future electricity grid in the upcoming two video lectures. The learning objective of the upcoming two video lectures are to understand the power and frequency control approaches of electricity grids and the impact of large-scale integration of photovoltaics in the electricity grid in terms of power and frequency management, forecasting approaches, harmonics, and the fast increasing share of photovoltaics itself in the energy system. In the first video, we will look at some principles of stabilizing an electricity grid. First, let's have a short recap of the various current systems that are being used. Direct current, abbreviated as DC, can be defined as an electric current that flows only in one direction. Direct current may flow through a conductor such as a wire, but can also flow through semiconductors, insulators, or even through a vacuum as electron or ion beams. The electric power is constant in time. Alternating current, abbreviated as AC, is defined as a periodic electric current that reverses direction. It can have different shapes. In traditional power system, it has a sinusoidal shape. Because the voltage of a single phase system reaches a peak value twice in each cycle, the instantaneous power is not constant. Active power is the usable power. It's the portion of power that produces a net transfer of energy in one direction every cycle. The load is able to use this power to do work. In DC, the power supplied by the load is the same power that is transferred towards the load when no losses are assumed. In AC, this is just a portion of the total power per cycle. So in contrast, reactive power is the portion of power that returns to the source in each cycle and therefore cannot be used by the load to do work. Reactive power is considered in AC. In this course, we will not deal with reactive power in great detail, but it is important to mention that the efficiency of the system increases as the reactive power flow decreases. Traditional power systems consist of an AC-based network. The grid works at constant frequencies at 50 Hz in large part of the world and 60 Hz in the Americas and parts of Asia. In order to avoid problems with the functioning of the load, frequencies must be uniform throughout an interconnected grid. Control loops mechanisms built into the power generation sources are able to maintain a balance between connected load and generation within a small deviation in frequency. Here we will shortly discuss some control loops mechanisms. In traditional power systems, the active power balance and the frequency is controlled by generators like shown in this picture. When losses are neglected, the active power balance can be expressed as the equation shown in the screen. The mechanical power supplied to the generator axis by the prime mover is equal to the electric active power, which is the output of the generator, plus the power accelerating or slowing down the generator. When the generated power and consumed power are in balance, then the mechanical power and the electric active power are equal and there is no accelerating power. Let's analyze what happens when a change occurs in the system. When a sudden increase of active power consumption of the load occurs and the mechanical power supplied to the generator remains constant, a decelerating power arises. When a decelerating power arises, it means that the rotation of the generator slows down and the frequency of the electric power output drops as well. In a traditional power system, a centrifugal governor controls the speed of a machine by regulating the amount of fuel that is supplied to it. In this way, a near constant speed independent of the load can be achieved. In the case of, for instance, steam engines, it regulates the emission of steam into the cylinder, as you can observe in this illustration. It is important to mention that frequency is a common parameter throughout the network. An increase of the active power consumption at a certain load point results in a reduction of the frequency in the whole system. The active power balance is restored by the speed governor. This action is called primary control. The speed governor can be set with a frequency power characteristics in order to do so. The frequency power characteristics, or droop, has a negative slope and is expressed as follows. The droop is the frequency drop in per unit of the rated frequency when the active power output of the generator rises from no load to full load. The droop characteristics is shown graphically at your screen. As you can observe, as the power increases, the frequency decreases. For a multi-generator system, the network power frequency characteristic is determined by the droop of the primary active power controls and the nominal rated power of all generators in the system. In such a case, a change in active power consumption is met by all the generators in the system, given as the combination of all droops as shown in the equation. The network power frequency characteristic lambda can be written as the negative of the change of power in the system divided by the change in frequency of the system. What does it mean? After primary control takes place, the power balance is restored at a lower or higher frequency, which is not a desirable operation condition. Secondary control brings back the system to the original frequency by increasing temporarily the prime mover power that raises the kinetic energy and therefore the frequency of the generating unit. It also allows to bring the tie line exchange of power back to the one that was agreed between the areas. An area can be a country, for example. In the figure you can observe how the secondary control is used to modify the setting of the speed governor in such a way that the frequency is brought back to the original reference. Now we understand how the power and the frequency of an AC power system is controlled. In the next video we will discuss what this means for the integration of photovoltaics in an electricity grid. So, see you in the next video.